title of this course is Probability and Statistics. So a question one might ask is, how exactly do you define statistics? Well, there are a number of different definitions that we could look at to define statistics. You see a couple on the screen. Statistics is sometimes thought of as a branch of mathematics, dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. The emphasis there is often on the mathematical part, and one of the things I like to make students aware of is that we will be using mathematics during this course, but statistics is not a math course. Sometimes people come in with the preconceived idea that statistics is just another mathematics course, but really statistics is a lot more than that. As you can see by this definition, we're going to focus on analysis, interpretation, presentation, all related to data. The second definition is maybe a little more closely aligned with my view of statistics: the science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring values in a whole from those in a representative sample. And I like the use of that term science because it implies a process. And one of the things that we want to do is develop a process that will help us when we receive new data to begin to draw information out of that data with the ultimate goal of using that data to help us drive business decisions. So really, statistics brings a number of different methods to bear. We'll use some mathematics, we'll use some scientific method, we'll bring all of that together with some data, we'll put a process around that to help us draw information out of that data, and then ultimately we'll use that data to help us drive decisions. And so that is the idea behind statistics, and we need probability to come alongside of statistics to help us quantify the uncertainty that's always present whenever we have data that we need to analyze. So before we begin to dive into the meat of the course, we're going to spend just a few minutes defining some definitions and talking about terminology. And we'll do this from time to time because statistics is a very broad discipline. It's a discipline that interacts with a lot of other disciplines in terms of the methodology that's used and the types of data that are analyzed. And so there are often multiple ways of referring to certain things in statistics, and there are words that we use for statistical analysis that may have a slightly different connotation in the context of our analysis versus other disciplines. So there are a number of definitions that we need to take a look at and some terminology, and once we get those established, then we'll be able to get on to some of the more fun elements of the course and dealing with data. The first two words that we need to define are population and sample, and these are terms that are going to follow us through the entire course. Population, most people have a general concept of population, and they tend to think of a population as being the number of people who live within a particular geopolitical region of the world. And that is certainly one definition of population, and in fact it's one population that may be of interest to us. But in statistics, population takes on a much broader connotation. The population for statistical analysis is the group of all individuals or all items of interest for our particular study. So if we're interested in understanding the public opinion of people in the United States when it comes to a political or economical or social type of scenario, then a population may refer to all of the individuals living in the United States. However, a population, if we are a computer manufacturer, may be all of the laptops that we produced from one of our manufacturing plants. If we're concerned perhaps about understanding the quality of those laptops, what is the percentage of defective screens that we might have generated whenever we were building the laptops, our population might be all laptops that were produced by a particular manufacturing company. If we're a pharmaceutical company and we're interested in developing a new drug to address some particular disease, perhaps we're looking at a drug that will help address complications associated with diabetes, then our population might be all individuals who have diabetes. So a population can mean a lot of different things, but we think about it in scope as the entire group of interest for our study. The challenge with the population is that typically it's very large. So if you think about the population of the United States or the population of China or the population of Germany, those are very large numbers. Given enough time and energy and resources, we could theoretically go out and collect information from everyone living in that geopolitical region. But there's a reason in the United States that the census is only done every 10 years. It's extremely time consuming, it's extremely costly, and therefore it's not something we want to do on a regular basis if we are really interested in trying to understand public opinion on the next greatest political candidate. So the population may be something that we could actually reach given time, energy, money, and so forth. But there's sometimes that the population, it may be impossible to collect information on every part of the population. The computer example, if we're looking at monitoring the number of defective screens on laptops from a particular computer manufacturing plant, our population of interest might be all of the laptops produced by that plant. That is an ongoing thing. There are more laptops being produced every day. It's almost impossible to think about grabbing information from every single laptop that's produced. Further, if we want to test those laptops, it requires doing some work to determine whether or not the laptop screen is defective. So that may require even somehow damaging the laptop in order to determine whether or not that screen is going to survive certain types of stresses. And so you don't want to take all of the laptops that are produced by your plant and put them through maybe a very stress-inducing test that could potentially damage the product that's being produced. So in that situation, it may not be even possible or plausible from a business perspective to collect information on every unit in the population. With our example looking at diabetes, we may have more of an ethical issue. If you have a new drug and you're trying to determine whether or not that new drug is going to be effective for treating a particular aspect of diabetes, you don't want to give that new drug to every single individual with that disease until you've done some work to determine whether or not the drug is going to be effective and to ensure that the drug is safe. So from an ethical perspective, it wouldn't make sense to give that drug to everyone in the population, to every individual who has diabetes, at least not in the initial data collection phases. So our population is large, it's often difficult, costly, and sometimes even impossible or not ethically plausible for us to collect information from the entire population. But those populations have what are called parameters of interest. So there is a true percentage of laptops that might be produced by our manufacturing company that will be defective. There is a true average income value for people living in the United States. If I had the time, the energy, the money, the resources, I could go out, I could collect information at a particular point in time, and I could come up with the true average income for people living in the United States. So that parameter is the true value of interest for some particular characteristic of that population. Again, it's a number that is fixed. It is typically unknown, but it's a number that we theoretically could compute based on the population if we had all of the information available. A sample is simply a representative subset of the population. It also could be very large. A sample does not have to be small. It could be a large sample, but it's just less than the population. So if we're trying to estimate the percentage of defective laptops, we might randomly select 100 laptops from a batch of laptops that have been produced over the course of a month, and we might test those 100 laptops to determine whether or not the screens are defective. So we draw a representative sample, and we'll talk more as we go through the course about how to make sure that that sample is representative. And we'll compute some quantity based on that sample. So we'll compute a sample proportion, for example, of the laptops that are defective. That quantity is computed based on that sample, and we'll use that information then to help us understand the population. That process of using sample information, of using a sample statistic to make some sort of a statement about the population parameters is called statistical inference. And a good portion of this course will be focused on statistical inference. How do we use the sample to make a statement about our population? How do we incorporate the uncertainty that is inherent in a sample to ensure that we have some boundaries when we're making our decisions? So we want to make decisions in the presence of uncertainty, uncertainty, we want to be able to quantify that uncertainty so we understand how reliable our decisions ultimately will be. But again, statistical inference is just taking information from that sample, typically a sample statistic, and using that sample statistic to provide a best guess or an estimate of our population parameter. That's where we're ultimately headed. It turns out that almost all of us do statistical inference on a fairly regular basis, whether we realize it or not. We live in a world, at least in a country in the United States, where polling is a daily occurrence. If there's an issue going on in the country, someone is taking a public opinion poll to try to determine how people feel about that issue. All of the major news agencies, Fox News, CNN, MSNBC, all of those news agencies, there are organizations like Rasmussen, that is a polling organization. Gallup is a polling organization. Quinnipiac University is a very reputable polling organization. They run out of their university. So all of these agencies are doing public opinion polls on a regular basis. And when you read a public opinion poll, you see headlines like the one on the screen. Voters are holding steady, financially optimistic about economy. And in that first paragraph, the mood of America is complicated. Most voters are optimistic about the economy as 3 in 10 see their wallet getting fatter, and so forth. And you can read the rest of what's on that slide, and you could even go and take a look at this poll online if you wanted to. The idea here is that the poll talks in very general terms, or the presentation of the poll talks in very general terms. And it seems to be saying that most voters in the United States of America are optimistic about the economy. It's a statement about the population. When we read that, our mind automatically makes that leap. We see the numbers, we see the margin of error and so forth on the polling information. But when we read a public opinion poll, we automatically make that leap of assuming these results are referring to the entire population. However, that's not what's happening here. If you read all the way to the bottom of the article, you'll see that they provide information on how the poll was actually conducted. And this particular poll was based on landline and cell phone interviews with 1,005 randomly chosen registered voters. So this is a sample. The information that we see here, those values of positive and negative feelings, they're based on information from 1,005 individuals, not from the entire population of the United States. But when we read those numbers, our mind makes that leap of assuming that that percentage of positive, that percentage of negative is referring to the entire United States, when in fact that number was actually computed based on a sample of 1,005 registered voters nationwide. We also can get a little bit more information here on exactly what the population is. The population here is not actually the entire United States. The population, in fact, is registered voters. They did not talk to people who were not registered voters, so they are not part of our population. So our population here actually is registered voters in the United States who have access to a landline or a cell phone. That's our population. The sample that was used to create the numbers that are presented here was 1,005 randomly selected registered voters from the United States. As we go through the course, we'll talk a little bit more about how polling organizations can get away with such a small sample. 1,005 individuals is a pretty small fraction of the number of people who live in the United States. So how can we make statements about the United States when we're only talking to 1,005 people? We'll also talk about where that margin of error comes from. What does it mean and how do we interpret that, and how can it help us as we try to use this information to move forward on some particular idea of interest. So all of us have done statistical inference. If you've ever read information about a public opinion poll and let your mind just go to the place where it assumes that information is talking about the entire country, that's exactly what you're supposed to do, and that is statistical inference. Now, there are a number of different types of data that we might encounter, and these definitions are not necessarily so important in and of themselves, but they are important because when we are presented with new data, the type of data will help instruct and guide us as to how we need to visualize and summarize that data. We have here 3 major types of data that we'll be considering. Nominal data are data that have labels or names to identify an attribute of an element. You could think about them almost like groups. They might be numeric or non-numeric, and we'll take a look at an example in just a second of all of these types of data. But you can think of nominal data almost like groupings, right? It could be red, yellow, blue, green. It could be age brackets. It could be anything that you can think of as falling into groups or categories or bins. And again, those groups or categories of bins can be represented with words, with characters, or they could be represented with numbers. Ordinal scale data is similar to nominal data in the sense that it is discrete. So you have discrete groups or values that you're interested in, but those values have some sort of meaningful rank or order. So something like a letter grade, A, B, C, D, F. That's a categorical style variable. They're discrete values for that variable, but an A is inherently better than an F. We know there's some rank ordering there. You could represent that ordinal scale with letters, or you could represent that ordinal scale with numbers, 4, 3, 2, 1, 0. Similarly, if you're looking at what's called a Likert scale, if you've ever taken a survey and you've been asked to rate on a scale of 1 to 5, with 1 being the worst and 5 being the best, and you're supposed to provide a rating, a Likert scale is a very common type of ordinal data. There is some inherent ranking there that 1 is not so good and 5 is very good. So those numbers, while they may be discrete, 1, 2, 3, 4, 5, there's an inherent ranking there. Interval scale data is just numeric data. So when we think about numbers, when we think about things like age or income or sales or weight, those kinds of variables where we can think about adding, subtracting, we can think about taking averages and totals, we can use them for mathematical computations. Those are what we would refer to as interval scale data. And again, it's what we would typically think of as just traditional numeric style data. Nominal and ordinal scale data are often referred to as categorical or sometimes qualitative, but generally referred to as categorical data. And interval scale data are often also referred to as quantitative data. So here's an example. This is some information, some stock market information. We have the company name, the stock market exchange, the ticker symbol for the company, and then we have some information on things like the market cap and the price to earnings ratio, as well as the profit rank. So if we were to rank these companies, and this is just a subset, a snapshot of these data, but if we were to rank these companies in terms of being the most profitable to the least profitable, what would that look like? We have all of these different columns of data. So if we wanted to find a nominal variable, something like the exchange, which stock exchange is the company listed in, that would be a nominal variable. There are certain values, Amex, OTC, NYSE, right? We have those discrete levels, and each one of those rows would fall into one of those buckets. So exchange would be a nominal variable. Market cap, or price to earnings ratio, or gross profit margin, those are interval valued variables. They're numbers, they're numeric. We could think about looking at the average market cap or the total gross profit margin across all of the companies. So those are interval valued or numeric or quantitative data. And then profit rank would be an ordinal valued variable, because again, these are discrete numbers, 1, 2, 3, 4, 5, but they're ranked according to some ordering based on their profitability. So 1 being the best and 10 being the worst. There's some inherent ordering. So we can see all of the different types of data that are represented there in this particular spreadsheet. Once we've established the kind of data that we're dealing with, then the next step in the process will be to begin to do some exploratory analysis. And exploratory analysis will lead us down the path of generating some graphs and some summary measures that will help us begin to get an overview or a broader understanding of the information contained in these data.